welcome to Deep Science Sleep. Find yourself in a comfortable position wherever you happen to be. Perhaps you're nestled beneath soft blankets, the weight of them creating a gentle pressure that tells your body it's safe to let go. Maybe you're listening in the quiet darkness of your room, where shadows soften the edges of familiar objects and the world beyond your window has grown hushed and still. Take a slow, deep breath. Feel your shoulders drop, your jaw unclench, your fingers uncurl. Tonight, we're going to explore one of the most mysterious and restorative processes that every human being experiences, the phenomenon of sleep. But we're not just going to learn about it. We're going to let the knowledge itself become a lullaby, each fact a soft wave washing over you, carrying you deeper into tranquility. Let yourself drift as we journey through the fascinating landscape of sleep, where your brain performs its nightly miracles and your body undergoes its essential restoration. The architecture of sleep. When you close your eyes at night and begin that gentle descent into unconsciousness, your brain doesn't simply switch off like a light. Instead, it embarks on a carefully choreographed journey through distinct stages, each one serving its own purpose in the grand symphony of rest. This progression happens not once, but multiple times throughout the night, creating what sleep scientists call sleep cycles. Understanding these cycles can be remarkably soothing, knowing that your brain has followed this same ancient pattern for as long as humans have existed. The moment you settle into bed and feel that first wave of drowsiness, you're entering what researchers designate as stage 1 of non-rapid eye movement sleep, or NREM sleep. This is the lightest phase of sleep, a threshold between wakefulness and true slumber, typically lasts only a few minutes, comprising roughly 5% of your total sleep time. During this transitional stage, your heartbeat begins to slow its pace, each pulse coming just a fraction more leisurely than the one before. Your breathing deepens and becomes more regular, no longer subject to the irregular patterns of conscious thought. Your muscles start to relax, releasing the tensions they've held throughout the day, though you might experience sudden muscle jerks called hypnic jerks, those startling sensations of falling that sometimes jolt you back toward wakefulness. These are completely normal, a remnant of our evolutionary past when our ancestors slept in trees and needed to catch themselves from falling. The electrical activity in your brain begins to shift during this first stage. If scientists were to attach electrodes to your scalp and measure your brain waves through electroencephalography, they would see the characteristic patterns changing from the beta waves of alert wakefulness to alpha waves. Alpha waves are relatively low in frequency, cycling between 8 and 13 times per second, and they're higher in amplitude than beta waves, meaning they create taller peaks and deeper valleys on the EEG readout. As you drift deeper into stage 1, even slower theta waves begin to appear, oscillating between 4 and 7 times per second. These theta waves will accompany you through much of your night's journey. Then you slip into stage 2, and here is where your brain begins to display some truly fascinating behavior. Stage 2 is still considered light sleep, but it's deeper than stage 1, and it comprises the largest portion of your night, about 45% of your total sleep time. You'll cycle through stage 2 multiple times during the night, and typically each round lasts a bit longer than the previous one. The temperature of your body core begins to drop during this stage, a necessary cooling that helps maintain the sleep state. Your heart rate continues its descent into slower rhythms, and your muscles relax even further. But the most interesting developments happen in your brain waves. Against the backdrop of those gentle theta waves, sudden bursts of rapid, high-frequency brain activity appear. These are called sleep spindles, and they're one of the most beautiful phenomena in sleep research. A sleep spindle lasts only a second or two, a brief firework of neural activity, and researchers believe these spindles may play a crucial role in learning and memory. They might be the brain's way of consolidating information, of deciding what from your day deserves to be kept and strengthened in your long-term memory. Alongside these spindles, you might also experience K-complexes, very high-amplitude patterns of brain activity that can occur spontaneously or in response to environmental stimuli. These K-complexes might serve as a bridge, keeping you connected to your surroundings just enough that important sounds, like a baby crying or an alarm, can still reach your awareness and bring you back to wakefulness if necessary. Stage 3 represents the deepest territory of non-rapid eye movement sleep, and this is where the magic of restoration truly begins. Adults spend about 25% of their total sleep time in this stage, though babies and children need considerably more, and as we age, we gradually require less. This stage is characterized by the appearance of delta waves, slow, powerful oscillations that roll through your brain like gentle swells on a calm ocean. These delta waves have a frequency of less than 3 cycles per second, and they have high amplitude, meaning they're strong, deep waves. When delta waves dominate your EEG, you're in what's commonly called slow-wave sleep or deep sleep, and this is the sleep from which it's hardest to wake. If someone tries to rouse you during stage 3, you might feel profoundly disoriented, experiencing what's known as sleep inertia, that foggy, confused state that can last up to half an hour. During this deep sleep, your body takes full advantage of your brain's profound rest. Growth hormone, which plays a vital role in tissue repair and muscle growth, is released in substantial quantities during slow-wave sleep. Your immune system strengthens its defenses, manufacturing proteins called cytokines that help fight infection and inflammation. The cellular repair mechanisms throughout your body kick into high gear, fixing the tiny damages accumulated during the day's activities. Even your bones benefit from this stage, as the processes of bone remodeling and strengthening are most active during deep sleep. For the first half of your night, stage 3 sleep tends to dominate, with cycles that might last 20 to 40 minutes at a time. But as morning approaches, these deep sleep periods become shorter and less frequent, eventually giving way to longer periods of lighter sleep and REM sleep. This gradual lightening of sleep toward morning is perfectly designed to ease you back toward wakefulness, rather than dragging you abruptly from the depths. After you've progressed through these 3 stages of NREM sleep, something remarkable happens. Instead of continuing deeper, your brain reverses course, typically moving back through stage 2 briefly before entering an entirely different realm, rapid eye movement sleep or REM sleep. This is where the landscape of sleep becomes truly extraordinary. REM sleep makes up about 25% of an adult's total sleep time, though in infants it comprises a much larger proportion. Your first REM period of the night might last only about 10 minutes, but each subsequent REM cycle grows progressively longer, with your final REM period potentially lasting an hour or more. During REM sleep, your brain becomes remarkably active. If you were to look at an EEG recording of someone in REM sleep and compare it to someone who's awake, you'd be hard-pressed to tell the difference. The brain waves during REM sleep look almost identical to waking brain waves. A mixed pattern of various frequencies, predominantly beta and gamma waves, indicating high levels of neural activity. This is why REM sleep is sometimes called paradoxical sleep. Your brain is highly active, almost as active as when you're awake, yet you're profoundly unconscious. The name rapid eye movement comes from one of the most distinctive features of this sleep stage. Beneath your closed eyelids, your eyes dart back and forth in quick, saccadic movements, as if you're watching some invisible scene unfold. These eye movements are conjugate, meaning both eyes move together in the same direction, and they seem to be connected to the visual imagery of dreams. If you were to wake someone during REM sleep, they would very likely report having been in the middle of a vivid, often bizarre dream. While dreaming can occur during other sleep stages, REM dreams are typically the most elaborate, emotional, and memorable. Perhaps the strangest feature of REM sleep is what happens to your voluntary muscles. The muscles you normally control consciously, like those in your arms, legs, and face. These muscles become temporarily paralyzed, a state called REM atonia. Only the muscles essential for life, those that control your breathing and heartbeat, remain active. This paralysis serves a crucial protective function, preventing you from physically acting out the often vigorous activities that occur in your dreams. Without this paralysis, you might literally start running, fighting, or performing whatever actions your dream self is engaged in, which could lead to injury. There's actually a sleep disorder called REM sleep behavior disorder, where this paralysis fails to occur, and people do act out their dreams, sometimes causing harm to themselves or their sleeping partners. Throughout the night, you typically complete 4 to 6 complete sleep cycles, each one lasting roughly 90 to 120 minutes. The exact length can vary from person to person and even from night to night, influenced by factors like age, recent sleep patterns, alcohol consumption, and overall health. The first cycle of the night is often the shortest, ranging from 70 to 100 minutes, while later cycles tend to settle into that 90 to 120-minute range. The composition of each cycle changes as the night progresses. During your first sleep cycle, you might spend a considerable amount of time in stage 3 deep sleep and only a brief period in REM sleep. But as dawn approaches, the pattern inverts. Deep sleep becomes scarce or absent, while REM periods grow longer and more frequent. This natural architecture means your early night sleep is dominated by physical restoration and immune function, while your late night and early morning sleep tilts toward memory consolidation, emotional processing, and dreaming. It's a beautiful design, really ensuring that both your body and mind receive the specific types of care they need. The chemical symphony of sleep. Sleep isn't just about brain waves and cycles. It's fundamentally a chemical process, orchestrated by a stunning array of neurotransmitters and hormones that flow through your brain and body. Understanding these chemical messengers can be deeply comforting, revealing that your desire to sleep isn't a weakness or laziness, but rather an elegant biological response to the needs of your nervous system. One of the most important chemicals in this symphony is adenosine, a molecule that accumulates in your brain throughout the hours you're awake. Adenosine is actually a byproduct of cellular metabolism. When your neurons burn energy in the form of adenosine triphosphate or ATP, they break down some of that ATP into adenosine. The longer you stay awake and the harder your brain works, the more adenosine builds up in certain regions, particularly in the basal forebrain. This accumulation of adenosine creates what scientists call sleep pressure or homeostatic sleep drive. Adenosine works by binding to specific receptors on neurons that promote wakefulness. When adenosine attaches to these receptors, it inhibits the firing of wake-promoting neurons, particularly those that produce other neurotransmitters like orexin and acetylcholine. It's like adenosine is gently pressing down on the accelerator of your consciousness, slowly but surely reducing the brain's ability to maintain alertness. The drowsiness you feel after a long day isn't just psychological tiredness. It's the direct result of adenosine levels rising to a point where they're actively telling your brain it's time to rest. This is also why caffeine is such an effective stimulant. Caffeine molecules have a similar shape to adenosine and can block adenosine receptors, preventing adenosine from binding and creating its sleep-promoting effects. When you drink coffee or tea, you're essentially putting up roadblocks that prevent adenosine from delivering its time-to-sleep message, at least temporarily. During sleep, particularly during slow-wave sleep, your brain clears away the accumulated adenosine. Levels gradually decrease throughout the night, which is why you wake up feeling refreshed and alert. Your sleep pressure has been reduced back to baseline. This adenosine system is one of the two major processes that regulate when you feel sleepy and when you feel alert, working hand in hand with your circadian rhythm to create your sleep-wake cycle. Another crucial player in sleep chemistry is melatonin, a hormone synthesized in a tiny pineal gland buried deep within your brain, about the size of a grain of rice. Melatonin production is exquisitely sensitive to light. Throughout the day, when light enters your eyes, it sends signals through your retina, along the optic nerve, to a cluster of neurons called the suprachiasmatic nucleus in the hypothalamus. This structure acts as your brain's master clock, synchronizing your body's rhythms with the 24-hour day. The suprachiasmatic nucleus, in turn, sends signals to the pineal gland, and in the presence of daylight information, it inhibits melatonin production. But as evening approaches and darkness falls, those inhibitory signals cease. The pineal gland begins to synthesize melatonin from serotonin, ramping up production dramatically. Melatonin levels in your bloodstream can increase tenfold or more during the night. This hormone doesn't necessarily make you sleep. It's more accurate to say it signals to your body and brain that it's nighttime, opening what researchers call the sleep gate. Melatonin helps reduce your core body temperature, a necessary step for sleep initiation. It also affects various brain regions involved in arousal, essentially telling them to quiet down. Some people describe taking melatonin supplements as not making them feel directly sleepy, but rather making them feel like it's biologically appropriate to sleep, which perfectly captures its role. Interestingly, norepinephrine plays a role in melatonin synthesis. Norepinephrine, also called noradrenaline, is released by neurons in a part of your brainstem called the locus coeruleus, and at night, norepinephrine from sympathetic nerve terminals stimulates the pineal gland through beta-2 receptors, triggering the cascade of chemical reactions that produce melatonin from serotonin. This is one of the beautiful interconnections in sleep chemistry. A neurotransmitter associated with arousal actually helps produce the hormone that promotes sleep, showing how these systems work together rather than against each other. Gamma-aminobutyric acid, better known as GABA, is the brain's primary inhibitory neurotransmitter, and it plays a starring role in initiating and maintaining sleep. Neurons that produce GABA are particularly concentrated in certain regions of the hypothalamus, especially an area called the ventrolateral preoptic nucleus. These GABAergic neurons are often called sleep-promoting neurons, and they do exactly what their name suggests. They promote sleep by inhibiting wake-promoting brain regions. When GABA is released from these sleep-promoting neurons, it binds to GABA receptors on wake-promoting neurons in various parts of the brain. These wake-promoting regions include the histaminergic neurons in the tuberomammillary nucleus, the noradrenergic neurons in the locus coeruleus, the serotonergic neurons in the raphe nuclei, the cholinergic neurons in the basal forebrain, and the orexinergic neurons in the lateral hypothalamus. By inhibiting all of these arousal systems simultaneously, GABA essentially puts the brakes on wakefulness. It's like a dimmer switch being slowly turned down, reducing the activity of arousal circuits and allowing sleep to occur. The mechanism by which GABA creates this inhibition is elegant in its simplicity. When GABA binds to GABA receptors on a neuron, it causes chloride ion channels in the cell membrane to open. Negatively charged chloride ions rush into the neuron, making the inside of the cell more negatively charged, a state called hyperpolarization. A hyperpolarized neuron is much less likely to fire an action potential, so the neuron becomes quiet, inactive. Multiply this effect across millions of neurons, and you have the widespread decrease in brain activity that characterizes sleep, especially the deep slow-wave sleep of stage 3. Many sleep medications, including benzodiazepines and so-called Z-drugs like zolpidem, work by enhancing the effects of GABA at these receptors, essentially amplifying your natural sleep-promoting mechanism. Serotonin's role in sleep is complex and somewhat paradoxical. This neurotransmitter, synthesized in neurons clustered in the raphe nuclei running through the brainstem, is involved in both promoting wakefulness and facilitating sleep, depending on which of its many receptor types are being activated and where in the brain we're looking. Generally speaking, serotonin neurons are most active during wakefulness, less active during NREM sleep, and nearly silent during REM sleep. Serotonin appears to support wakefulness by maintaining a general level of arousal and by inhibiting REM sleep. During waking hours, serotonin release helps maintain muscle tone and contributes to alertness. But as you enter NREM sleep, serotonin activity begins to decrease. During REM sleep, serotonergic neurons stop firing almost entirely, and this cessation is actually necessary for REM sleep to occur. If serotonin levels remained high, they would prevent the muscle atonia and other characteristics of REM sleep. Perhaps most importantly, serotonin serves as the precursor molecule for melatonin. In the pineal gland, an enzyme called tryptophan hydroxylase first converts the amino acid tryptophan into 5-hydroxytryptophan, which is then converted into serotonin by another enzyme. At night, when the proper signals arrive from the suprachiasmatic nucleus, yet another enzyme called N-acetyltransferase modifies serotonin to produce melatonin. This means the same molecule that helps keep you alert during the day is chemically transformed into the hormone that tells your body it's time for sleep. A perfect example of biological economy and elegance. Acetylcholine, a neurotransmitter used by neurons in several brain regions including the basal forebrain and parts of the brainstem, has a fascinating relationship with sleep stages. Acetylcholine levels are high during waking, when the brain needs to be alert and process sensory information. They drop significantly during NREM sleep, especially during slow-wave sleep when sensory processing is minimized and the brain is in its deepest rest. But then, during REM sleep, acetylcholine levels surge again, reaching levels similar to or even higher than waking levels. This cholinergic activation during REM sleep is thought to contribute to the generation of the intense, vivid dreams characteristic of the sleep stage, as well as the fast, wake-like EEG patterns. The muscle paralysis of REM sleep is partly maintained by the high acetylcholine levels activating certain receptors in the spinal cord that suppress motor neuron activity. Orexin, also called hypocretin, is a neuropeptide discovered relatively recently in the late 1990s, but it's proven to be crucial for maintaining stable wakefulness. Orexin is produced by a relatively small group of neurons in the lateral hypothalamus, but these neurons send projections throughout the brain, connecting to most of the major arousal systems. Orexin acts like a stabilizer or reinforcer of the wake state. When orexin neurons are active, they help coordinate and maintain the activity of histaminergic, noradrenergic, serotonergic, and dopaminergic wake-promoting systems. It's as if orexin provides a steady underlying push toward wakefulness, keeping all the arousal systems working together. During sleep, orexin neuron activity decreases dramatically. This makes sense. If orexin promotes wakefulness, it needs to be quiet for sleep to occur. The sleep-promoting GABAergic neurons in the ventrolateral preoptic nucleus inhibit orexin neurons, and adenosine also suppresses their activity. The importance of orexin becomes starkly clear in narcolepsy, a neurological condition where people experience sudden, uncontrollable bouts of sleepiness and can fall asleep at inappropriate times. Research has shown that people with narcolepsy type 1 have lost most or all of their orexin-producing neurons, likely through some form of autoimmune attack. Without orexin's stabilizing influence on wakefulness, the boundary between sleep and wake becomes unstable, leading to the characteristic symptoms of narcolepsy. This discovery has led to new treatments for insomnia, medications called dual orexin receptor antagonists that block orexin signaling, essentially removing some of the arousal pressure and making it easier to fall asleep. The hormone cortisol follows a strong circadian rhythm, typically reaching its lowest point in the middle of the night and then beginning to rise in the early morning hours, reaching peak levels shortly after you wake up. This morning rise in cortisol, sometimes called the cortisol awakening response, helps mobilize energy stores, increases alertness, and prepares your body for the day ahead. Cortisol has a complex relationship with sleep. Normal nighttime levels are low and compatible with sleep, but abnormally high cortisol, such as during periods of chronic stress, can interfere with sleep initiation and disrupt sleep architecture, reducing time spent in slow-wave sleep and REM sleep. Growth hormone shows the opposite pattern to cortisol. In children and adults alike, the most significant pulse of growth hormone release occurs during the first cycle of deep slow-wave sleep, typically within the first hour or two after falling asleep. This growth hormone surge facilitates protein synthesis, tissue repair, and, in children and adolescents, actual physical growth. Even in adults who have stopped growing taller, growth hormone remains crucial for maintaining muscle mass, bone density, and cellular repair. This is one reason why getting adequate deep sleep, especially in the first part of the night, is so important for physical recovery, wound healing, and athletic performance. These various neurochemicals don't work in isolation. They form an intricate network of interactions, a push and pull between arousal and sleep systems. Researchers often describe it using the metaphor of a seesaw or a flip-flop switch. On one side are the wake-promoting systems: orexin, histamine, norepinephrine, serotonin, acetylcholine, and dopamine. On the other side are the sleep-promoting systems: GABA, adenosine, and various sleep-promoting peptides. When wake-promoting systems are active, they inhibit sleep-promoting systems, keeping you alert. When sleep-promoting systems gain the upper hand, they inhibit wake-promoting systems, allowing sleep to occur. The brilliance of this mutual inhibition is that it creates relatively stable states. You're usually clearly either awake or asleep, rather than stuck in some uncertain middle ground. The transitions happen relatively quickly, like a switch flipping, though various factors can influence how smoothly those transitions occur. The body's restoration during sleep. While your brain cycles through its stages of electrical activity and neurochemical shifts, your body is hard at work performing essential maintenance and repair. Sleep is far from a passive state for your physical systems. It's an active period of restoration that touches virtually every tissue and organ in your body. One of the most fundamental restorative processes during sleep involves your muscles. Throughout the day, physical activity creates microscopic damage to muscle fibers, tiny tears in the protein filaments that allow muscles to contract. This is normal and even desirable, as it's part of how muscles grow stronger. But for repair and growth to occur, your body needs time when those muscles aren't being actively used. During sleep, particularly during slow-wave sleep, growth hormone and testosterone levels rise, signaling muscle cells to begin repair processes. Satellite cells, specialized stem cells associated with muscle tissue, activate and begin fusing with damaged muscle fibers, adding new nuclei and facilitating the synthesis of new contractile proteins. Inflammatory signaling decreases during sleep, allowing muscle tissue to recover from the day's work. This is why athletes often emphasize the importance of sleep for performance. Without adequate rest, muscles cannot fully repair and strengthen, leading to fatigue, reduced performance, and increased injury risk. Your immune system undergoes significant enhancement during sleep. The production of cytokines, small proteins that regulate immune function and inflammation, increases during sleep, particularly during slow-wave sleep. Some cytokines are pro-inflammatory, helping to coordinate the immune response against infections or injuries. Others are anti-inflammatory, helping to resolve inflammatory responses once they've served their purpose. The balance and timing of these cytokine releases are crucial for proper immune function. T cells, a type of white blood cell critical for targeting and destroying infected cells, show enhanced efficiency during sleep. When you're asleep, T cells better integrate signals about potential threats, improving their ability to attach to and destroy infected cells. Research has shown that even a single night of sleep deprivation can significantly impair immune function, reducing the number of natural killer cells in your bloodstream and impairing the production of antibodies in response to vaccination. Conversely, getting adequate sleep in the days following vaccination enhances antibody production and immune memory, making the vaccine more effective. Throughout your body, cells undergo repair and renewal continuously, but these processes are enhanced during sleep. Cellular organelles damaged by oxidative stress during waking hours are broken down and recycled through a process called autophagy. New organelles are synthesized to replace them. DNA repair mechanisms work more efficiently during sleep, correcting mutations and damage that accumulated during the day. This cellular housekeeping is crucial for preventing the accumulation of damaged components that could eventually lead to cellular dysfunction or death. The cardiovascular system receives a break during sleep. Your heart rate slows, typically dropping by 10 to 30 beats per minute compared to resting waking levels. Blood pressure decreases, a phenomenon called nocturnal dipping. This nightly reduction in blood pressure is essential for cardiovascular health. People who don't show proper nocturnal dipping, whose blood pressure remains relatively high during sleep, have increased risk for heart disease, stroke, and other cardiovascular problems. The heart itself benefits from this reduced workload, as do blood vessel walls, which experience lower stress and have opportunity for repair. Your metabolic systems also use sleep time for important regulation. Glucose metabolism is modulated during sleep, with insulin sensitivity showing specific patterns across different sleep stages. During slow-wave sleep, glucose uptake by the brain decreases since neural activity is reduced, allowing for better blood sugar regulation. The balance between hunger-regulating hormones shifts during sleep. Leptin, which signals satiety, increases, while ghrelin, which stimulates hunger, decreases. This hormonal balance helps ensure you don't wake up constantly with hunger pangs. When sleep is disrupted or insufficient, this hormonal balance is disturbed, with leptin decreasing and ghrelin increasing, which can lead to increased appetite and food intake the following day. This is one mechanism linking chronic sleep deprivation with weight gain and metabolic syndrome. Body temperature regulation follows a distinctive pattern during sleep. Your core body temperature begins to decrease as you approach sleep, reaching its lowest point in the early morning hours, typically around 4 or 5 in the morning. This temperature drop of roughly 1 to 2 degrees Fahrenheit is not just a consequence of rest. It's an active process that helps initiate and maintain sleep. The cooling occurs partly through increased blood flow to your extremities, your hands and feet. You might have noticed that your feet often feel warm as you're falling asleep. This is because blood vessels in your skin are dilating, allowing more warm blood from your core to flow to the surface where heat can radiate away. This is why having cold feet can make it harder to fall asleep. Your body is trying to cool your core temperature, but if your feet are cold, the blood vessels constrict, preventing this heat dissipation. Some people find that wearing loose socks or placing a hot water bottle near their feet helps them fall asleep faster by promoting vasodilation and core cooling. Perhaps one of the most fascinating aspects of sleep's restorative power involves a recently discovered system called the glymphatic system. This waste clearance system, first identified in 2012, functions like a plumbing system for the brain, flushing away cellular debris and toxic metabolic byproducts that accumulate during waking hours. The glymphatic system gets its name from its similarity to the lymphatic system that drains waste from other parts of the body, combined with its dependence on glial cells, particularly astrocytes, in the brain. Here's how it works. Cerebrospinal fluid, the clear liquid that surrounds your brain and spinal cord, flows along the outside of arteries as they penetrate into the brain tissue. This cerebrospinal fluid then exchanges with the interstitial fluid, the fluid that fills the spaces between brain cells. The interstitial fluid, now carrying dissolved waste products from cellular metabolism, flows along the outside of veins as they exit the brain, carrying the waste products toward the lymphatic vessels in the neck where they can be eliminated from the body. The astrocytes facilitate this fluid exchange through water channels called aquaporin, for channels that are densely packed in their end feet wrapped around blood vessels. The remarkable finding is that the glymphatic system is dramatically more active during sleep than during wakefulness, perhaps 10 times more active. During sleep, particularly during slow-wave sleep, the spaces between brain cells expand by about 60%. This expansion dramatically reduces resistance to fluid flow, allowing cerebrospinal fluid to sweep through the brain tissue more efficiently. At the same time, norepinephrine levels decrease during sleep, and this drop in norepinephrine causes the blood vessels to relax and dilate slightly, further enhancing fluid flow. The glymphatic system also increases cerebrospinal fluid production during sleep. What wastes does the glymphatic system remove? Among the most important are proteins that can misfold and aggregate, potentially contributing to neurodegenerative diseases. Beta amyloid, the protein that forms plaques in the brains of Alzheimer's disease patients, is cleared by the glymphatic system during sleep. So is tau protein, another protein associated with Alzheimer's disease, and alpha-synuclein, the protein that aggregates in Parkinson's disease. During waking hours, as your brain cells are active, they produce these proteins as normal byproducts of cellular function. But if these proteins are allowed to accumulate without being cleared away, they can begin to clump together and become toxic to neurons. Sleep provides the opportunity for this essential waste removal. The discovery of the glymphatic system helps explain why chronic sleep deprivation or poor sleep quality is associated with increased risk for neurodegenerative diseases. If you consistently don't get adequate sleep, particularly deep slow-wave sleep when glymphatic function is at its peak, these toxic proteins may accumulate faster than they can be cleared, potentially contributing to neurodegeneration over time. It also provides a compelling biological explanation for why we need to spend roughly 1/3 of our lives asleep. Our brains need that time for essential cleaning and maintenance that cannot be adequately performed while we're awake. Studies using advanced imaging techniques have confirmed glymphatic function in living human brains, showing that tracers injected into cerebrospinal fluid travel through the brain tissue in patterns consistent with glymphatic flow. Moreover, research has found that glymphatic function decreases with age, which may partly explain why older adults often have more disturbed sleep and are at higher risk for neurodegenerative diseases. Scientists are now exploring ways to enhance glymphatic function, including investigating whether certain sleep positions might optimize the system, whether specific types of exercise can improve it, and whether some medications or interventions might boost its activity. Memory, learning, and the sleeping brain. One of the most profound things sleep does for you is consolidate and optimize your memories. Learning doesn't end when you close your textbook or leave the rehearsal space. Your brain continues processing and strengthening what you learned during your subsequent sleep. This isn't a vague, metaphorical process. It's a precise neurobiological phenomenon that scientists can measure and observe. During waking hours, when you learn something new, whether it's a fact, a skill, or an experience, your brain creates an initial memory trace primarily in a seahorse-shaped structure called the hippocampus, buried deep in your temporal lobes. The hippocampus specializes in rapidly forming new memories, acting like a temporary buffer. But these hippocampal memories are fragile. Without further processing, they would fade. This is where sleep comes in, transforming those fragile short-term memories into stable long-term memories through a process called systems consolidation. During slow-wave sleep, particularly during stage 3 deep sleep, a remarkable phenomenon occurs. Your hippocampus begins to replay the patterns of neural activity that occurred during your waking experiences. If you spent time during the day learning the layout of a new building, walking through its corridors and noting landmarks, the specific sequence of neurons that fired while you navigated will fire again during your slow-wave sleep, but in fast-forward, replaying your experience at a compressed timescale. This replay happens during brief events called sharp-wave ripples. Bursts of high-frequency oscillatory activity in the hippocampus that last only about 50 to 100 milliseconds but occur dozens or hundreds of times during a night's sleep. These sharp-wave ripples are often coordinated with two other types of brain oscillations: sleep spindles and slow oscillations. The slow oscillations are the characteristic slow waves of deep sleep, large-scale electrical waves that roll across the cortex roughly once per second. Sleep spindles are those brief bursts of 12 to 15 cycle per second activity you learned about earlier. The current model suggests that slow oscillations originate in the cortex and travel down to the thalamus, triggering sleep spindles. Both of these help create windows of opportunity when the cortex is particularly receptive to input from the hippocampus. When a sharp wave ripple occurs in the hippocampus during one of these receptive windows, the memory information is transmitted from the hippocampus to the neocortex, where it can begin to form more permanent, distributed representations. Over the course of many nights of sleep, through countless replay events and information transfers, the memory gradually becomes less dependent on the hippocampus and more integrated into cortical networks. What starts as a specific episodic memory in the hippocampus can become a more generalized semantic knowledge in the cortex. The details of where and when you learn something may fade, but the essential information becomes part of your enduring knowledge base. This transformation isn't just about moving memories from one brain region to another. It's about abstracting key principles, recognizing patterns, and integrating new information with what you already know. Different types of memories benefit from different sleep stages. Declarative memories, facts and events that you can consciously recall, show the strongest benefits from slow-wave sleep, with its replay mechanisms and hippocampal cortical dialogue. Procedural memories, skills and habits that you perform without conscious thought, like playing a musical instrument or riding a bicycle, show strong benefits from REM sleep and stage 2 sleep. Studies of musicians learning new pieces have found that the skills show marked improvement after a night of sleep, even without additional practice. The improvements are specifically correlated with the amount of stage 2 sleep obtained, suggesting that the sleep spindles during this stage may be packaging and optimizing procedural memory. Motor learning appears to benefit from a sequence where slow-wave sleep provides initial stabilization and REM sleep provides subsequent enhancement and integration. The synaptic homeostasis hypothesis offers another lens through which to understand sleep's role in memory. During waking hours, learning strengthens synapses, the connections between neurons. With each new experience and piece of information, more synapses are strengthened through a process called long-term potentiation. This strengthening involves physical changes. Synapses grow larger, add more receptors, create new connections. It's essential for learning, but there's a problem. If synapses just keep getting stronger and stronger without any counterbalancing process, they would eventually become saturated, unable to strengthen further. The brain would lose its capacity to learn new things. Additionally, maintaining all these strengthened synapses requires substantial energy and cellular resources. According to the synaptic homeostasis hypothesis, sleep serves as a period of synaptic downscaling or renormalization. During sleep, particularly during slow-wave sleep, synaptic connections are globally weakened or downscaled. This doesn't mean all memories are erased. Rather, the brain proportionally reduces synaptic strength across the board, maintaining the relative differences between synapses while bringing the overall level back down to a sustainable baseline. The strongest, most important synapses, those associated with significant or repeatedly encountered information, are downscaled less than weaker synapses, or may even be further strengthened in some cases. The weakest synapses, those associated with unimportant or irrelevant information, may be pruned away entirely. This selective preservation and elimination helps improve the signal-to-noise ratio in your neural networks, making important memories stand out more clearly while clearing away the clutter of unnecessary information. Evidence for synaptic homeostasis comes from multiple sources. Measurements of synaptic size and strength in animal brains show that synapses are, on average, larger and stronger after waking periods than after sleeping periods. Molecular markers associated with synaptic strength follow similar patterns. The slow waves of deep sleep appear to be particularly important for this downscaling. The slow oscillations may help coordinate the weakening of synapses across large areas of cortex simultaneously. This process serves not only to maintain the capacity for future learning but also to save energy. Smaller, weaker synapses require less energy to maintain, and the brain, despite representing only about 2% of your body weight, consumes roughly 20% of your total energy. Any process that can make neural networks more efficient provides significant benefits. Sleep also appears to enhance creativity and insight. There's a reason why people talk about sleeping on a problem. During sleep, particularly during REM sleep, the brain may explore unusual combinations of ideas, forming connections that wouldn't occur during logical, focused waking thought. REM sleep is associated with reduced activity in the prefrontal cortex, the region involved in logical thinking, planning, and inhibition, while other brain regions remain active. This combination may allow for more free-form association between different pieces of information, potentially leading to creative insights. Studies have shown that people are better at solving problems requiring creative insight after REM sleep than after wakefulness or other sleep stages. The classic example is Auguste Kekulé's discovery of the ring structure of benzene, which reportedly came to him in a dream. While we can't know how many such stories are accurate or how common this phenomenon truly is, controlled laboratory studies do support the idea that sleep, particularly REM sleep, can facilitate creative problem-solving. Emotional memories receive special processing during sleep. Experiences that had strong emotional content, whether positive or negative, are more likely to be consolidated and retained than neutral experiences. During REM sleep, the emotional tone of memories appears to be processed and sometimes softened. The amygdala, a brain structure crucial for emotional processing, shows high activity during REM sleep, but the dorsal anterior cingulate cortex and other prefrontal regions that might normally modulate emotional responses show reduced activity. Some researchers propose that this pattern allows the brain to process and integrate emotional experiences while reducing their emotional charge. You essentially remember the content of an emotional event while the raw emotional intensity fades somewhat. This overnight emotional blunting can be adaptive, helping you learn from emotional experiences without being overwhelmed by them. However, if sleep is disrupted shortly after a traumatic experience, this emotional processing may not occur properly, potentially contributing to conditions like post-traumatic stress disorder. where emotional memories retain their full intensity and continue to trigger strong reactions. The relationship between sleep and emotional regulation extends beyond memory processing. Sleep deprivation significantly impairs your ability to regulate emotions the following day. After a night of poor sleep, the amygdala shows heightened reactivity to negative stimuli, roughly 60% greater activation in sleep-deprived individuals compared to well-rested ones. At the same time, the connections between the amygdala and the prefrontal cortex, which normally help regulate emotional responses, become weakened. This combination means that sleep-deprived individuals tend to have stronger emotional reactions, particularly negative ones, and less ability to modulate those reactions. You've probably experienced this yourself. Everything seems more frustrating, more overwhelming, more emotionally charged when you're tired. Getting adequate sleep helps restore normal emotional regulation, keeping your reactions proportional to the actual situations you encounter. Sleep before learning is also important, not just sleep after learning. A well-rested brain is better prepared to form new memories. Studies have shown that sleep deprivation before attempting to learn new information impairs the ability to encode that information, potentially reducing learning efficiency by up to 40%. The hippocampus, your brain's memory encoding center, appears to need adequate sleep to maintain its ability to form new memory traces. After sleep deprivation, hippocampal activity patterns during learning tasks are disrupted, and the formation of new synaptic connections is impaired. In practical terms, this means that pulling an all-nighter before an exam is particularly counterproductive. Not only do you miss the memory consolidation that would occur during sleep after studying, but your sleep-deprived brain is also less capable of learning the material in the first place. The benefits of sleep for learning and memory aren't limited to a single night. Sleep quality and quantity over weeks and months shape your cognitive abilities. Students who maintain regular sleep schedules and get adequate sleep consistently perform better academically than those with irregular schedules or chronic sleep restriction, even when total sleep hours over a week are equated. The consistency and timing of sleep matter, not just the quantity. This is likely because your brain's memory systems work best when operating on a predictable rhythm, with regular opportunities for consolidation and renewal. Interestingly, targeted memory reactivation has emerged as a technique to enhance specific memories during sleep. In these experiments, researchers exposed sleeping individuals to cues that were associated with specific learning during wakefulness. For example, if you learned the locations of objects while each object was paired with a particular sound, playing those sounds again during your subsequent slow-wave sleep can enhance your memory for those object locations. The sounds, played softly enough not to wake you, appear to trigger replay of the associated memories, giving them preferential consolidation. While this technique is still primarily a research tool, it hints at the possibility of optimizing learning through strategic enhancement of sleep-based memory processing. Dreams and the theater of sleep. As you drift through the landscapes of sleep each night, your mind creates its own private cinema, projecting vivid narratives, bizarre scenarios, and emotional journeys that you experience as dreams. For most of human history, dreams were mysterious, their purpose and meaning subject to wild speculation, religious interpretation, and psychological theory. Modern neuroscience has begun to illuminate the mechanisms behind dreaming, revealing it to be a natural consequence of specific brain states, while still preserving much of its wonder. Dreams can occur during any sleep stage, but they vary dramatically in their characteristics depending on when they occur. Dreams during NREM sleep, particularly during stage 2 and stage 3, tend to be more thought-like, less vivid, and more fragmented. If awakened from slow-wave sleep and asked if they were dreaming, many people report something like thinking about work or vague impressions or sometimes nothing at all. The content is often mundane, closer to ordinary waking thoughts than to what we typically think of as dreams. REM sleep is where dreams become extraordinary. The dreams that occur during REM sleep are typically vivid, bizarre, emotionally intense, and story-like. They have visual imagery so clear and detailed that you might not realize you're dreaming at all. They incorporate multiple senses. You might hear conversations, feel textures, experience motion. The narratives of REM dreams often have a hallucinatory quality, with impossible events accepted without question, sudden scene changes, and violations of physical laws that don't seem strange within the dream itself. Characters may morph from one person to another. You might find yourself flying, or discover you can breathe underwater. And within the dream, these impossibilities seem perfectly normal. The neurobiology of REM dreams helps explain these characteristics. During REM sleep, visual and motor areas of your cortex become highly active, while the dorsolateral prefrontal cortex, responsible for logic, planning, and reality testing, shows markedly reduced activity. This combination means your brain is generating vivid sensory experiences and narratives without the usual executive oversight that would recognize impossibilities or maintain logical consistency. The visual cortex, particularly the extrastriate visual areas involved in processing complex visual scenes, shows activity patterns similar to those during waking vision. This is why dream imagery can be so detailed and realistic. The motor cortex also activates as if you're performing the actions in your dream, but thanks to the muscle paralysis of REM sleep, these motor commands don't reach your muscles. The emotional centers of your brain, particularly the amygdala and the anterior cingulate cortex, are highly active during REM sleep. This helps explain why dreams often have strong emotional content. Fear, joy, anxiety, excitement, or sadness that can feel as intense as waking emotions. The amygdala's activation during dreams may be why nightmares, which are most common during REM sleep, can be so powerfully frightening. Interestingly, the emotions in dreams don't always match the content in logical ways. You might dream of a threatening situation but feel calm, or dream of a mundane event but feel intense anxiety. This disconnect may reflect the fact that emotional activation during dreams isn't necessarily responding to the dream content in the same causal way it would during waking life. Rather, both the emotions and the narrative may be semi-independent products of different brain regions' activities. The hippocampus plays a complex role in dreaming. While it's active during dreams, dreams typically don't create lasting episodic memories the way waking experiences do. You've surely noticed that most dreams are forgotten within minutes of waking, even if they seemed incredibly vivid and memorable during the dream itself. This may be because the neurochemical environment during REM sleep isn't conducive to forming new long-term memories. In particular, norepinephrine levels are at their lowest during REM sleep, and norepinephrine appears to be necessary for converting short-term memories into stable long-term memories. Your brain is experiencing and processing during dreams, but it's not efficiently recording those experiences for later retrieval. What purpose do dreams serve? This remains one of the most debated questions in sleep research. Several theories have substantial evidence supporting them, and it's quite possible that dreams serve multiple functions simultaneously. The threat simulation theory proposes that dreams, particularly anxiety dreams and nightmares, serve as a kind of overnight training program for dealing with threats. By simulating dangerous or challenging situations in the safe environment of sleep, your brain may be rehearsing responses and strengthening the neural circuits involved in threat perception and defensive behaviors. Consistent with this theory, dreams frequently contain threatening content: being chased, falling, being attacked, or finding yourself in dangerous or embarrassing situations. From an evolutionary perspective, individuals who used sleep time to practice threat responses might have had survival advantages. The emotional regulation theory suggests that dreams help process emotional experiences, particularly negative ones. During REM sleep, as mentioned earlier, you reactivate emotional memories in a context where stress hormones like norepinephrine are absent. This allows your brain to work through emotional content without becoming overwhelmed by the associated stress response. The dream narrative might weave together current concerns with past experiences and general fears, creating a kind of emotional stew that your brain can process and, hopefully, resolve or at least reduce in intensity. This would explain why dreams so often incorporate themes related to your current life stressors: an upcoming exam, a relationship conflict, or work pressures, mixed with seemingly random elements from memory. The memory consolidation theory focuses on dreams as a window into the memory processing that occurs during sleep. According to this view, the content of dreams reflects the reactivation and reorganization of memories. The bizarre, associative nature of dreams may result from the brain making new connections between different memories, searching for patterns, and integrating new experiences with existing knowledge. The strange combinations in dreams, your childhood home combined with your current workplace, or a friend who looks like someone else entirely, might reflect the memory networks being reshuffled and reorganized. While the dream narrative itself may not be meaningful, the underlying process of memory reactivation and consolidation certainly is. The default mode network theory proposes that dreams represent the activity of the brain's default mode network, a set of brain regions that activate when you're not focused on the external world, such as during rest or mind wandering. During waking life, the default mode network is involved in self-referential thinking, autobiographical memory, imagining the future, and considering the perspectives of others. During REM sleep, this network remains active, but without the usual constraints and reality checking provided by external sensory input and prefrontal executive control. Dreams might be the brain's default mode of operation, creating self-relevant narratives from the building blocks of memory and imagination. Some researchers take a more deflationary view, suggesting that dreams are simply epiphenomena, byproducts of sleep processes that serve other functions. According to this view, the brain activity during REM sleep serves important purposes like memory consolidation and emotional processing, and dreams are just what it feels like, subjectively, for these processes to occur. The narrative and imagery of dreams might be your cortex's attempt to make sense of random activation patterns, without the dreams themselves serving any particular function. This activation synthesis hypothesis, proposed by Alan Hobson and Robert McCarley, suggests that the brainstem generates semi-random activation during REM sleep, and the cortex synthesizes this activation into the best coherent narrative it can construct, resulting in the bizarre, disconnected nature of dream plots. Regardless of their ultimate purpose, Dreams have certain consistent features across individuals and cultures. Most dreams occur in familiar settings. Your home, your workplace, places from your past. Most dream characters are people you know or have encountered, though they may appear in unusual combinations or contexts. Dreams are typically experienced from a first-person perspective, with you as the protagonist, though occasionally you might observe yourself from an outside perspective. Physical laws are often violated in dreams. You might fly, walk through walls, or find that objects transform. But social and emotional rules tend to be preserved. People in dreams behave in socially recognizable ways, even if the situations are impossible. Lucid dreaming represents a fascinating variant where you become aware that you're dreaming while still asleep. During a lucid dream, you retain some degree of critical thinking and awareness even while experiencing the dream imagery. Some lucid dreamers can exert intentional control over their dream content, deciding where to go, what to do, or how the narrative unfolds. Neuroimaging studies of lucid dreaming have found increased activity in the frontopolar cortex and other prefrontal regions compared to normal REM dreaming. This suggests that lucid dreaming represents a hybrid state where some aspects of waking consciousness, particularly self-awareness and metacognition, coexist with the vivid imagery and reduced critical thinking of REM sleep. Learning to have lucid dreams is possible through various techniques. Reality testing, where you habitually check during waking life whether you're dreaming by trying to push your finger through your palm or reading text twice to see if it changes, can carry over into dreams, triggering lucidity. The mnemonic induction of lucid dreams technique involves setting a strong intention before sleep to recognize when you're dreaming. Wake back to bed methods, where you wake after several hours of sleep and then return to sleep with the intention of becoming lucid, can be particularly effective. Some people use external cues like specific patterns of lights or sounds delivered during REM sleep to trigger lucid awareness. Sleep paralysis, while often frightening when it occurs, is another window into the mechanisms of REM sleep. Sleep paralysis happens when the muscle atonia of REM sleep persists even as you wake up, leaving you conscious but temporarily unable to move. This usually lasts only seconds to a few minutes, but it can feel much longer and can be accompanied by a sense of pressure on your chest, difficulty breathing, and often vivid hallucinations. These hallucinations commonly include sensing a presence in the room, seeing shadowy figures, or feeling like someone or something is holding you down. These experiences are so consistent across cultures that many societies have developed folklore about them. Succubi and incubi in European tradition, the old hag in Newfoundland, Kanashibari in Japan. The hallucinations during sleep paralysis likely result from the same mechanisms that produce dreams. Your brain is still partly in a REM-like state, generating vivid sensory experiences, but you're conscious and aware of your actual environment. The sensing of a presence and the typical threatening nature of the hallucinations might reflect amygdala activity combined with the disturbing experience of being unable to move, which your brain may interpret as a threat. Understanding that sleep paralysis is a benign if unsettling phenomenon, a temporary mismatch between REM mechanisms and awakening, can make the experience less frightening if it occurs. Sleep across the animal kingdom. Sleep is not uniquely human, nor even uniquely mammalian. The need for sleep, or at least for rest states that share many of sleep's characteristics, appears to be nearly universal across the animal kingdom, from the simplest organisms to the most complex. Exploring how different species sleep reveals both the fundamental importance of sleep and the remarkable ways evolution has adapted sleep to fit different ecological niches. Mammals display an enormous range of sleep patterns and durations, shaped by factors like predation risk, feeding requirements, body size, and metabolic rate. At one extreme are the champion sleepers. The brown bat sleeps roughly 19 to 20 hours per day, spending the vast majority of its life unconscious. Giant armadillos sleep about 18 hours daily. Possums, sloths, and pythons similarly spend most of their time asleep, typically between 15 and 18 hours out of every 24. These long sleep durations are often associated with low metabolic rates, limited predation risk when hiding in secure locations, and diets that don't require constant foraging. At the opposite extreme are animals that seem to barely sleep at all. Giraffes hold the record for the shortest sleep duration among land mammals, sleeping only around 4.5 hours per day, often in brief bouts of just a few minutes at a time. This remarkably short sleep duration is thought to be driven by several factors. Their large body size requires substantial food intake, necessitating many hours of feeding each day. Their long necks make lying down both difficult and risky, as getting back up takes time, during which they're vulnerable to predators. And as highly visible prey animals in relatively open habitats, extended periods of unconsciousness would be extremely dangerous. Elephants similarly sleep only about 3 to 4 hours per day, spending much of their time foraging to meet their enormous caloric requirements. Most mammals, including humans, fall somewhere in the middle of this spectrum. Dogs sleep about 12 to 14 hours per day, though in shorter bouts spread throughout the day and night. Cats sleep about 15 hours daily, maintaining their reputation for laziness, though their sleep is often quite light and easily interrupted. Primates generally sleep between 9 and 15 hours, with humans at the shorter end of that range. Interestingly, humans appear to sleep less than most other primates but spend a greater proportion of our sleep time in REM sleep, leading some researchers to suggest that human sleep became more efficient through evolution, packing more of the restorative benefits into less total sleep time. Marine mammals face a unique challenge. They breathe air, but they live in water. How can they sleep without drowning? Different marine mammal species have evolved different solutions to this problem. The most remarkable is unihemispheric slow-wave sleep, where only one half of the brain sleeps at a time while the other half remains awake. Dolphins and porpoises use this strategy, allowing one brain hemisphere to rest while the other maintains enough awareness to surface for breathing, watch for predators, and navigate. You can actually observe this if you watch a dolphin sleeping. One eye will be closed while the other remains open, and the dolphin will slowly swim in circles, always turning in one direction. After some time, the dolphin will switch, closing the other eye and circling in the opposite direction, as the sleeping and waking hemispheres swap roles. Northern fur seals exhibit even more flexibility. When they're at sea, they use unihemispheric sleep like dolphins, keeping one hemisphere awake to maintain swimming and breathing. But when they come onto land, where they don't need to consciously control breathing and face different dangers, they switch to bihemispheric sleep, sleeping with both brain hemispheres simultaneously, just like terrestrial mammals. This represents a remarkable adaptability in sleep architecture, switching between two fundamentally different sleep patterns depending on environmental demands. Birds face similar challenges to marine mammals during long-distance migration. How do birds that fly nonstop for days or weeks at a time get the sleep they need? Evidence suggests that some migratory birds also use unihemispheric sleep, allowing them to rest one brain hemisphere at a time while maintaining flight with the other. Frigate birds, which can stay airborne for weeks during ocean crossings, have been shown through miniaturized EEG recording devices to engage in brief periods of sleep while flying, with either one or both hemispheres sleeping. Remarkably, these birds sleep far less while flying than when on land, only about 42 minutes per day versus about 12 hours on land, suggesting they can function with extremely reduced sleep for extended periods when necessary, though they likely need to make up for this sleep debt once they reach their destination. Even among birds that don't migrate extreme distances, sleep patterns vary widely. Small passerine birds typically sleep about 12 to 14 hours per day, usually in a single long overnight bout synchronized with darkness. Larger birds like chickens sleep about 8 to 10 hours. Some birds, like the common swift, are thought to sleep predominantly on the wing, spending almost their entire lives airborne except during the breeding season. Birds generally experience both NREM and REM sleep, though their REM sleep is brief and may look somewhat different from mammalian REM sleep. During avian REM sleep, muscle tone decreases and there may be rapid eye movements, but the episodes are typically very short, lasting only a few seconds rather than the minutes-long REM periods common in mammals. Reptiles and amphibians show sleep-like states, though it becomes increasingly difficult to definitively identify true sleep as we move further from mammals. Lizards and snakes show periods of behavioral quiescence when they're less responsive to stimuli, their metabolic rate decreases, and they adopt specific sleep postures, often finding hidden, protected locations. Some reptiles show something resembling REM sleep, with increased brain activity and slight movements during certain rest periods, though this remains debated. Crocodilians have been observed with one eye open during rest, suggesting they might employ a form of unihemispheric sleep, keeping partial vigilance even while resting. Turtles show clear rest activity cycles and prefer to rest in sheltered locations, but whether they experience distinct sleep stages similar to mammalian sleep remains unclear. Amphibians like frogs definitely rest and show circadian rhythms of activity, becoming quiet and unresponsive during their inactive periods. They'll adopt specific postures, often partially burying themselves or hiding under vegetation, and their responsiveness to stimuli decreases. However, the brain wave patterns that characterize mammalian sleep stages are absent or very different in amphibians, making it difficult to classify their rest as true sleep in the neurological sense. This raises interesting questions about what defines sleep. Is it the behavioral state of reduced responsiveness and specific postures? Or does it require specific neurological signatures like slow waves and sleep spindles? Fish present perhaps the most ambiguous case. Many fish species show clear rest periods when they remain still, often in sheltered locations, and their responsiveness to stimuli decreases. Zebrafish, a common laboratory model, show rest periods with many sleep-like characteristics. They're more difficult to arouse during rest, they show rebound rest after rest deprivation, and their rest is regulated by circadian rhythms and homeostatic sleep pressure. Some fish rest while floating motionless, others settle on the bottom, and some actually sleep inside crevices or buried in sand. Parrotfish famously secrete a mucus cocoon around themselves before sleeping, possibly to mask their scent from predators. Even more remarkably, Sleep or sleep-like states appear to exist in invertebrates. Fruit flies show clear rest periods with all the hallmarks of sleep. They're harder to arouse during rest, they need more rest after being kept active, and they die more quickly under sleep deprivation than under starvation. Honeybees show sleep-like behavior, becoming immobile with lowered antennae and reduced body temperature during rest periods, and young bees learning new tasks show increased sleep time. Octopuses, those remarkably intelligent invertebrates, show active and quiet sleep states, and during active sleep, they change colors and textures in patterns that suggest they might be dreaming about their environment. Jellyfish, lacking anything resembling a centralized brain, still show pulsing behavior that decreases at night in a rhythm that appears to be sleep, and they're harder to arouse from this state. This near universality of sleep or sleep-like states across the animal kingdom, from jellyfish to humans, strongly suggests that sleep serves fundamental biological functions that are so important they've been preserved throughout hundreds of millions of years of evolution. Whatever sleep does, whether it's cellular maintenance, waste clearance, memory processing, or some combination of functions, it appears to be so crucial that virtually no complex organism can survive without it. Every creature needs its rest in one form or another. Environmental and cultural sleep. The way humans sleep has changed dramatically throughout history and continues to vary significantly across cultures and geographic locations. Understanding these variations reveals that many aspects of sleep we consider natural or inevitable are actually culturally constructed, opening possibilities for thinking differently about our own sleep patterns. Before the advent of artificial lighting, human sleep patterns were necessarily synchronized with the natural cycles of light and dark. Historical records, diaries, and literature from pre-industrial Europe suggest that people commonly practiced what's called segmented sleep or biphasic sleep. Instead of sleeping in one consolidated 8-hour block, people would sleep in two distinct periods separated by a period of wakefulness. Typically, they would fall asleep an hour or two after sunset, sleep for 3 to 4 hours in what was called first sleep, then wake for 1 to 2 hours around midnight. During this wakeful period, people engaged in various activities: quiet household tasks, prayer or meditation, conversation with bedmates, or intimacy. Then they would return to bed for second sleep, another 3 to 4 hour period, waking around dawn. References to first and second sleep appear throughout historical documents from the medieval period through the early 19th century. Medical texts from this era discuss the optimal timing for prayer or medicine taking during the interval between sleeps. Legal depositions mention events occurring during the waking period between sleeps. The practice was so common that it often went unremarked, mentioned in passing as an obvious part of the rhythm of night. Researchers who've studied these patterns suggest that consolidated monophasic sleep, our current norm of sleeping in one long block, may have emerged only after the widespread adoption of artificial lighting made it possible and socially acceptable to stay awake longer into the evening, pushing back the beginning of sleep and compressing the night into a single sleep period. Experimental studies have added support to the idea that biphasic sleep might be a natural human pattern. When people are placed in environments without artificial light, following natural light-dark cycles, some, though not all, spontaneously develop segmented sleep patterns. This suggests that our biology may retain some flexibility in sleep timing and structure, with the particular pattern that emerges depending on environmental and social cues. Across contemporary cultures, sleep practices vary enormously. the timing of sleep, the social context of sleep, and attitudes towards sleep differ in ways that can seem strange to those raised in Western industrialized societies. Many Mediterranean and Latin American cultures practice siesta, an afternoon nap that complements a shorter nighttime sleep period. In these cultures, businesses often close during the hottest afternoon hours, allowing people to rest and avoid the least comfortable time of day for work. While often stereotyped as laziness, the siesta pattern actually aligns well with natural circadian rhythms. Many people experience an energy dip in the early afternoon, sometimes called the post-lunch dip, and a brief nap can enhance alertness and performance for the rest of the day. In many parts of Asia, co-sleeping, where children sleep in the same room or even the same bed as their parents, is the norm, often continuing well into childhood. This contrasts sharply with the Western, particularly American, emphasis on independent sleep in separate rooms from early infancy. Neither approach is inherently correct or incorrect from a sleep biology perspective, though they may carry different implications for parent-child attachment, nighttime parenting, and sleep quality for both parents and children. Parents in co-sleeping cultures report it makes nighttime care easier and strengthens family bonds, while advocates of independent sleep emphasize its role in fostering self-soothing and independent sleep skills. The physical environment in which you sleep has profound effects on sleep quality. Temperature is one of the most critical factors. Your core body temperature needs to drop by about 1 to 2 degrees Fahrenheit for sleep initiation to occur smoothly. The optimal ambient temperature for sleep is typically between 60 and 67 degrees Fahrenheit, though individual preferences vary. Temperatures significantly above or below this range can fragment sleep and reduce time spent in slow-wave sleep and REM sleep. Your body accomplishes the necessary core cooling partly by radiating heat from your skin, which is why having cool air circulating around you helps, and why heavy, non-breathable bedding can interfere with sleep. Your extremities play a special role in temperature regulation during sleep. As mentioned earlier, your hands and feet warm up as you're falling asleep because blood vessels in your skin dilate, allowing warm blood from your core to flow to your periphery where heat can radiate away. This is why cold hands and feet can delay sleep onset. The blood vessels are constricted, preventing effective core cooling. Some sleep researchers recommend taking a warm bath or shower 1 to 2 hours before bed. The bath warms your core initially, but as you cool down afterward, the dilation of peripheral blood vessels persists, enhancing the heat dissipation that facilitates sleep. Light exposure dramatically affects sleep through its influence on circadian rhythms and melatonin production. Light, particularly the blue wavelengths abundant in daylight and electronic screens, sends signals through your eyes to the suprachiasmatic nucleus, your brain's master clock. Exposure to bright light, especially blue light, suppresses melatonin production and can shift your circadian rhythm. Morning light exposure helps advance your rhythm, making you sleepy earlier the next evening, while evening light exposure delays your rhythm, making you sleepy later. In our modern environment, evening exposure to bright indoor lighting and electronic screens can significantly delay sleep timing and reduce sleep duration. Creating darkness in your sleeping environment is equally important. Even modest light exposure during sleep can suppress melatonin, fragment sleep, and reduce slow-wave sleep. Room darkening curtains, eye masks, or simply eliminating light sources like digital clocks or LED indicators can improve sleep quality. Some people are more sensitive to light during sleep than others, but complete darkness appears to optimize sleep for most individuals. This makes evolutionary sense. For the vast majority of human history, nights were profoundly dark aside from starlight and moonlight, and our sleep systems evolved in that context. Sound also affects sleep quality, though the relationship is complex. Constant background noise can fragment sleep and prevent deep sleep, particularly if the noise is intermittent or unpredictable. Sudden loud noises can cause brief arousals or full awakenings. However, some forms of steady, predictable sound can actually improve sleep for some people by masking other disruptive noises. White noise, which contains all frequencies at equal intensity, or brown noise, which emphasizes lower frequencies, can create a steady acoustic environment that helps some people fall asleep and stay asleep. The effectiveness of these sounds likely varies based on what you've become habituated to and your individual sensitivity to noise. Altitude affects sleep in interesting ways. At high altitudes, the reduced oxygen availability triggers changes in breathing patterns. Many people experience periodic breathing at altitude, where breathing alternates between deep breaths and very shallow breaths or even brief pauses. This periodic breathing can fragment sleep and reduce sleep quality, particularly during the first few nights at altitude. The reduced oxygen also tends to increase the proportion of lighter sleep stages and reduce REM sleep and slow-wave sleep. Acclimatization gradually improves sleep at altitude, though even well-acclimated individuals may never sleep quite as well as they do at sea level. This is one reason why high-altitude mountaineers often report profound exhaustion. They're not just working hard physically, but also getting poor quality sleep night after night. Seasonal variations in sleep have been documented across many cultures. Some research suggests that humans naturally sleep slightly longer during winter months with longer nights, and slightly shorter during summer with longer days. This aligns with the sleep patterns of many animals that show distinct summer and winter sleep durations. In modern industrialized societies with artificial lighting and climate control, these seasonal variations have been dampened but not eliminated. Some people experience seasonal affective disorder during winter months, characterized by depression, increased sleep duration, and difficulty waking, possibly representing an exaggerated version of normal seasonal sleep changes. The healing power of sleep. When we talk about the healing power of sleep, we're not speaking in metaphors or gentle platitudes. We're talking about something as fundamental to your survival as the air you breathe. Sleep is the body's master restoration protocol, the nightly maintenance system that determines not just how you'll feel tomorrow, but how long you'll live, how healthy you'll remain, and how gracefully you'll age. Let's start with perhaps the most compelling reason to prioritize your sleep: your lifespan itself. Research involving over 172,000 adults has revealed something extraordinary. Men who consistently achieve quality sleep live approximately 5 years longer than those who don't. For women, the benefit is about 2 years. Think about that for a moment. 5 additional years of life, gained simply by honoring your body's need for rest. 5 more years of sunrises, of laughter with loved ones, of experiences and memories yet to be created. But it's not just about the quantity of sleep. Recent studies have shown that sleep regularity may be even more important than duration. People with consistent sleep patterns show a 20 to 48% lower risk of death from all causes compared to those with irregular sleep schedules. Your body craves rhythm, predictability, that ancient circadian dance that aligns you with the natural world. When you sleep at 7 hours but at wildly different times each night, you're sending your biological systems into chaos. When you maintain that steady rhythm, sleeping and waking at consistent times, you're supporting every system in your body. The sweet spot appears to be 7 to 8 hours for most adults, though this can vary slightly from person to person. Studies tracking over 1 million people found that those sleeping less than 6 hours faced a 12% greater risk of death, while those sleeping more than 9 hours faced a 30% increase. It's a U-shaped curve, a Goldilocks zone where your body finds its perfect balance of restoration without oversleeping into the realm of diminishing returns. Now let's talk about your mind, that intricate landscape of thoughts and emotions that colors every moment of your waking life. Sleep and mental health share a bidirectional relationship so intertwined that researchers often struggle to determine which comes first. What we do know is that the connection runs deep. People with insomnia are 10 times more likely to have depression and 17 times more likely to experience anxiety compared to those who sleep well. 10 times, 17 times. These aren't minor correlations. These are the kinds of statistics that should make us reconsider sleep as optional, as something we can sacrifice for just one more episode, one more scroll through social media, one more hour of work. But here's where it gets fascinating. When researchers improve people's sleep through cognitive behavioral therapy, their depression and anxiety symptoms improve as well. The bigger the improvement in sleep quality, the bigger the reduction in mental health symptoms. This suggests that sleep isn't just a symptom of mental illness, but potentially a cause, and more importantly, a treatment avenue. During sleep deprivation studies, otherwise healthy people experience increased anxiety and distress after just one poor night of rest. Their emotional regulation falters. Small frustrations become major irritations. Neutral faces start to look threatening. The emotional centers of the brain become hyperactive while the prefrontal cortex, our rational control center, loses its ability to keep those emotions in check. Quality sleep acts as a buffer against stress and negative experiences. During the COVID-19 pandemic, researchers found that people with good sleep quality maintained better mental health despite unprecedented levels of chronic stress. High-quality sleep helped build resilience, creating a protective shield against depression and anxiety even when the world felt uncertain and overwhelming. There's also the matter of sleep timing. Fascinating research on over 75,000 people in the United Kingdom revealed that going to bed early and waking early is better for mental health, even for natural night owls. Those who went to bed late showed higher risks of depression, anxiety, and other mental health disorders, regardless of their natural sleep preferences. Your circadian rhythm has preferences, and working against it comes at a cost. Now consider pain, that unwelcome companion that affects millions of people worldwide. Between 67 and 88% of individuals with chronic pain experience sleep disruption, and at least 50% of people with insomnia report chronic pain. But which comes first? Recent research provides a surprising answer. Sleep disturbances appear to be a stronger predictor of pain than pain is of sleep problems. When you're sleep deprived, your pain threshold drops dramatically. Studies show that experimental sleep deprivation reduces pain tolerance and increases pain sensitivity. One particularly striking study found that just 3 hours of sleep per night for 2 nights in a row reduced skin elasticity and made wrinkles more noticeable, but it also made people more sensitive to pain. Conversely, when researchers extended sleep to 10 hours per night in mildly sleepy individuals, pain tolerance increased by 20%. The mechanisms are complex but fascinating. Sleep deprivation appears to reduce the effectiveness of the body's natural pain inhibition systems, particularly those involving endogenous opioids. It also increases inflammatory markers like interleukin-6 and C-reactive protein, which are pain-facilitating agents. Poor sleep creates a neurological environment where pain signals are amplified and pain relief systems are suppressed. For people living with chronic pain conditions, sleep becomes even more critical. Sleep problems predict the development of fibromyalgia, migraines, back pain, and widespread chronic pain. Preoperative sleep disturbances predict both acute post-surgical pain and the risk of developing chronic post-surgical pain. The relationship creates a vicious cycle. Pain disrupts sleep. Poor sleep increases pain sensitivity, which causes more sleep disruption, which further increases pain. Breaking this cycle often requires addressing sleep as aggressively as the pain itself. Let's turn to something more visible, more immediate, your skin. The concept of beauty sleep has been dismissed as folklore for generations, but modern science has vindicated this ancient wisdom with remarkable precision. During deep sleep, your body releases growth hormone, with approximately 70% of the daily secretion occurring in the first half of the night, particularly during slow-wave sleep stages. This hormone drives collagen synthesis, the protein responsible for keeping skin firm, elastic, and youthful. When you consistently go to bed late, missing that critical window between 10 p.m. and 2 a.m. when cellular repair peaks, you're not just losing sleep hours. You're missing the richest, most valuable portion of your skin's repair cycle. Blood flow to your skin increases during sleep, delivering oxygen and nutrients while removing metabolic waste products. This increased circulation allows skin cells to repair damage from UV exposure, pollution, and daily environmental stressors. The body's antioxidant production ramps up during sleep, protecting skin from free radical damage. Meanwhile, cortisol levels drop to their lowest point between 2 and 4 a.m. This stress hormone breaks down collagen and increases inflammation when elevated. Lower cortisol during sleep protects your existing collagen, reduces inflammatory skin conditions, and supports the skin barrier function that keeps moisture in and irritants out. Sleep-deprived individuals show visible signs of accelerated skin aging. Research has documented increased fine lines and wrinkles, uneven pigmentation, reduced elasticity, and sagging skin in people who consistently sleep poorly. They also show decreased ability to recover from sun exposure, with more sluggish healing from sunburn. Even short-term sleep restriction of just 5 hours per night significantly reduces skin elasticity compared to 7 or more hours. Poor sleep impairs skin hydration by increasing transepidermal water loss, leaving skin drier and more vulnerable to damage. It disrupts the skin's natural barrier function, making it more susceptible to irritation and environmental assault. The skin's moisture balance, carefully regulated during sleep, becomes compromised. Studies on collagen supplementation have found that sleep quality may enhance the benefits of oral collagen. While supplementation shows promise for skin elasticity and hydration, Researchers suggest that good sleep amplifies these effects by supporting immune function and reducing oxidative stress. Your nighttime skincare routine matters, certainly, but nothing replaces the fundamental restorative work your skin accomplishes during quality sleep. For athletes and anyone engaged in regular physical activity, sleep represents perhaps the single most important recovery tool available. During deep sleep stages, particularly slow-wave sleep, your body prioritizes tissue repair, muscle recovery, and the production of growth hormone. Research on elite athletes reveals that sleep extension improves performance across multiple domains. Basketball players who increased their sleep showed 9% improvement in free throw and three-point accuracy, along with better sprint speeds. Tennis players demonstrated enhanced serve accuracy. Swimmers showed improved kick-stroke efficiency and turn performance. Cognitive functions like reaction time, decision-making, and judgment all improved with adequate sleep. The flip side is equally dramatic. Sleep deprivation decreases running performance, reduces muscle glycogen concentration, and impairs submaximal strength. Studies document decreased isokinetic peak torque, reduced minute ventilation, diminished distance covered, slower sprint times, and reduced time to exhaustion. Athletes sleeping fewer than 7 hours the night before testing perform worse on neurocognitive assessments. During sleep, your body replenishes muscle glycogen stores, the critical energy source depleted during exercise. One study found that 30 hours of sleep deprivation compared to 8 hours of sleep resulted in significantly lower muscle glycogen concentrations before exercise, demonstrating the body's inability to fully recover without adequate rest. Human growth hormone, essential for tissue repair and muscle growth, is secreted almost exclusively during deep sleep. Without sufficient deep sleep, this growth hormone production is limited, reducing your body's ability to recover and build muscle efficiently. Protein synthesis, the process of rebuilding damaged muscle fibers, reaches its peak during sleep, making a strong case not only for prioritizing rest, but also for consuming protein before bed to support overnight recovery. Sleep also regulates the hormonal environment crucial for athletic performance. Adequate sleep lowers cortisol levels and reduces systemic inflammation, creating ideal internal conditions for healing and recovery. Sleep deprivation, by contrast, elevates cortisol, promotes fat storage over muscle building, and increases inflammation throughout the body. For injury prevention, sleep's role cannot be overstated. When you're tired, coordination errors multiply, form deteriorates, and reaction times slow, all increasing injury risk during training. Insufficient sleep hinders tissue repair, meaning muscles, joints, and tendons don't fully recover before the next session. This cumulative strain dramatically increases the likelihood of muscle pulls, strains, and joint-related injuries. Athletes who sleep fewer than 8 hours per night show significantly higher injury rates compared to those who sleep 8 or more hours. Finally, let's address perhaps the most sobering aspect of sleep's healing power: its role in preventing cognitive decline and dementia. As our population ages, Alzheimer's disease and other forms of dementia represent some of our most feared health outcomes. The good news is that emerging research suggests quality sleep may be one of our most powerful protective factors. Studies tracking thousands of people over years and decades have revealed compelling associations. People who consistently sleep fewer than 5 hours per night are twice as likely to develop dementia and twice as likely to die compared to those sleeping 6 to 8 hours. Research following nearly 8,000 participants found that consistently sleeping 6 hours or less at ages 50, 60, and 70 was associated with a 30% increase in dementia risk compared to sleeping 7 hours. The mechanisms appear to involve beta-amyloid, the protein that clusters and clumps to form Alzheimer's plaques. During waking hours, your brain produces this protein as part of normal function. During sleep, particularly deep sleep, brain cells and their connections actually shrink slightly. This shrinkage creates more space between cells, allowing beta-amyloid and other metabolic waste products to be flushed away through the glymphatic system, essentially the brain's waste clearance network. When you don't get enough sleep, or when sleep quality is poor, this crucial cleaning process is compromised. Beta-amyloid accumulates, day after day, year after year, gradually building toward the threshold where dementia symptoms emerge. Recent research from UC Berkeley has shown that superior amounts of deep, slow-wave sleep can act as a protective factor against memory decline even in people with existing high amounts of Alzheimer's pathology. Deep sleep acts like a life raft, keeping memory afloat despite the weight of disease pathology. The quality of sleep matters enormously. Research has shown that fragmented sleep, characterized by frequent awakenings throughout the night, shows stronger associations with cognitive decline than sleep duration alone. People with high levels of sleep fragmentation were 2 to 3 times more likely to score below average on tests of executive function, working memory, processing speed, and global cognition compared to those with less fragmented sleep. Sleep disorders compound the risk. Obstructive sleep apnea increases dementia risk through intermittent oxygen deprivation and its impact on cardiovascular health. Insomnia's relationship with Alzheimer's appears tied to increased inflammation and impaired glymphatic clearance. Studies show that each 1% decrease in deep sleep per year is connected with a 27% increase in dementia risk and a 32% increase in Alzheimer's risk. But here's the hopeful part. Unlike many cognitive reserve factors such as years of education or early life experiences, sleep is modifiable. You can change your sleep habits. You can prioritize rest. You can create environments and routines that support deep, restorative sleep. Treating sleep disorders through interventions like CPAP therapy for sleep apnea or cognitive behavioral therapy for insomnia shows promise for improving cognitive performance and potentially reducing dementia risk. The restorative nature of quality sleep extends across every system in your body, from the molecular level to whole organ function. It regulates hormones that control appetite, metabolism, stress response, and immune function. It consolidates memories and processes emotions. It clears metabolic waste from the brain and repairs cellular damage throughout the body. It rebuilds muscle tissue and strengthens bones. It maintains skin barrier function and produces collagen. It calibrates pain perception and supports mental health resilience. Quality sleep is not a luxury. It's not something to be sacrificed when life gets busy or demanding. It is fundamental to human health, as essential as nutrition, as critical as exercise, as necessary as the very air we breathe. And so we arrive at the end of our journey through the remarkable world of sleep. But really, it's just the beginning. Because tonight, when you lay your head upon your pillow and feel your body begin to relax, you'll do so with new understanding. You'll know that your body is about to embark on its nightly restoration, that complex symphony of repair and renewal that unfolds in the darkness. You'll know that as you drift into those first stages of sleep, your brain will begin consolidating the day's memories, filing away experiences and lessons learned. You'll know that your growth hormone will surge during those precious deep sleep stages, rebuilding muscle tissue, strengthening bone, and stimulating collagen production in your skin. You'll know that your glymphatic system will begin its crucial work, flushing away the metabolic waste that accumulated during your waking hours, potentially protecting you from cognitive decline decades from now. You'll understand that every night of quality sleep is an investment in your future self, that the 7 or 8 hours you commit to rest tonight will echo through tomorrow, through next week, through the months and years ahead. That prioritizing sleep isn't selfish or lazy, but rather one of the most responsible, health-promoting choices you can make. Think of sleep as your body's master reset button, pressed each night to clear away the day's accumulated stress, to repair what was damaged, to prepare you for whatever tomorrow might bring. It's the foundation upon which all other health behaviors rest. Without adequate sleep, even the healthiest diet and most dedicated exercise routine cannot fully optimize your health. So tonight, as you prepare for sleep, create your sanctuary. Dim the lights in the hour before bed, signaling to your circadian system that day is ending. Set aside the screens and their blue light that confuses your internal clock. Perhaps lower the temperature in your bedroom, allowing your core body temperature to drop as nature intended. Consider a warm bath or shower, which paradoxically helps you cool down more quickly once you're out, facilitating that temperature drop that promotes sleep. Breathe deeply, feeling your chest rise and fall, your heart rate beginning to slow. Release the tensions of the day, the worries and responsibilities that seemed so urgent just hours ago. Trust that your body knows what to do, that it has performed this nightly miracle countless times before and will do so again. If you found value in this exploration of sleep's profound importance, if you've discovered insights that might change how you think about rest and recovery, please consider liking this video and subscribing to our channel. We create content like this regularly, diving deep into the science of sleep and exploring the fascinating mechanisms that govern human health and well-being. Share this knowledge with others who might benefit. Sleep deprivation has become so normalized in our modern world that many people don't realize the profound impact their poor sleep habits may be having on their health, their longevity, their cognitive function, their emotional well-being. As you close your eyes tonight, rest well knowing that every moment of quality sleep is a gift you're giving to your body, your mind, and your future. Sweet dreams, and may your sleep be deep, restorative, and healing in every way that matters. Sleep well, friends. Until next time.